Hello everyone, my name is Luc Hendricks. I'm with NLNet Labs and I'm here today with Willem to talk about the XDPeriments we did. We've been tinkering with DNS and XDP and would like to share our first results on that. So, why XDP? I'm sure you've heard about several programmable data plane technologies in recent years. I'm sure you've heard about P4 and I'm also quite sure you've heard about XDP. And they are popular, and that's for a good reason, because these technologies give you a certain flexibility in your data plane without sacrificing too much of performance. And specifically, when using XDP on your Linux machine, it's an easy way to perform some parts of what you want to do with incoming packets in your kernel, do some heavy lifting, if you will, and still have some traditional user space software after that. And I think that's the most important thing, the most important takeaway of this presentation. And the thing we realized after working for almost a year with XDP now is that you can use XDP to augment what you already are doing on your system. You don't have to replace everything that you're doing in user space. You don't have to replace your entire DNS name server or resolver. And the focus in this presentation to show you what we do is response rate limiting. We'll take that as a use case and show how you can make a drop-in in XDP to perform response rate limiting in your kernel. So, just to be on the same page with everyone, response rate limiting 101. If we see too many incoming queries, we want to respond either with a truncated DNS answer or we want to drop it. And we track the number of queries per second, ideally per the source IP, so where the queries are coming from, or the source prefix. Now, for the other things that we need to know to understand everything in this presentation, what's BPF, what's XDP? I assume most of us understand what DNS is. BPF, or actually eBPF, that's let's call it an evolution of the traditional Berkeley packet filter that I guess everyone knows from their TCP dump filters when running TCP dump. Now, it's a bit of a deceiving name, if you ask me, because it's much more than a packet filter nowadays. And actually, if people talk about BPF, if folks say BPF now, they mean the extended BPF. If you want to talk about the classic BPF, that's how we call it nowadays, CBPF. Everything in this presentation is about eBPF, but we'll say BPF. What's XDP? XDP is the Express Data Path, which is a network driver hook that lets you run BPF code exactly there in your driver. So that means we can run arbitrary code in kernel space, so in the driver, before anything happens with the Linux network stack. So before a socket buffer is actually allocated. So how do we run code? How do we let it interact with the rest of the stack? If we look at the classic stack, we have the NIC, we have the driver, we have the network stack on top of that, and with sockets we communicate with the applications, right? There's no XDP here. If we have XDP, we determine the packet's destiny based on the return codes from our piece of BPF code. So for example, on the left here, we have a XDP TX return code, which basically means send this out of the same NIC again. Other option is XDP drop, which, well, no surprise, drops the packet. And this is very simple stuff, but I hope you can imagine that this already enables you to do quite some cool things, right, without going up to user space. We can still go up to user space. If we decide that our code needs to punt this packet upwards, we can still do this. We can punt it up the network stack and make it go to a authoritative name server, NSD, for example. Or, and we're not using this in this example, but just for completeness sake, we can return XDP redirected to send it out of another NIC. And we have a special case of XDP redirect where we can send it to a special type of socket. In this case, you will need to adapt your user space application to actually choose this type of socket, but then you can bypass the entire Linux network stack. So that's interesting for performance reasons. So one more time, what we're focusing on here today is we try to augment DNS software, existing running DNS deployments, if you will, by using a subset of the return codes I just explained. So we can drop certain things, we can send it back out of the NIC, or we can actually pass it on to something running on the operating system. We are not focusing on adapting existing software to use the special AF XDP sockets, and we're not going to re-implement everything in XDP. Now, typical workflow when doing anything in XDP, the BPF code you write is actually C code. We compile it, and this is important. If your code compiles, it does not mean that it will work, because in the next step, and this might be the most frustrating step when you do anything with XDP, you will try to load the just compiled code, which runs the verifier. It's a special BPF verifier that checks whether your code will actually terminate and whether it's not too complex, so whether it will terminate soon enough. So very complex code with many instructions will not be allowed to load on that interface. And that makes perfect sense because you're trying to run arbitrary code in kernel space. We cannot have kernel panics just because you made a mistake in your piece of networking code that you try to load on the interface. If there's no objections by the verifier, the code is active on the interface, again, only on ingress, so incoming packets are processed by your just loaded code. No mod probing, no reboot, no reconfiguration of anything, right? So it's as simple as this. If you're running a recent Linux kernel, you can do this. And if you need any further configuration or interaction with that code in kernel space, that goes via BPF maps. We'll get to that. So response rate limiting. What does this code look like? The code is online on GitHub. You can check it out. But high-level view, we have to parse the packet. So is it Ethernet, IP, and UDP with a destination port 53, obviously. And we check whether the payload is actually a correctly formatted DNS query. If not, we just pass it on because it's probably something else and we're not going to process it. Now we know that we're dealing with an actual DNS query. We have to do the state keeping. So we're going to calculate the query rate from this specific source address. And we're keeping the state using maps. And based on the rate, we make a decision. Are we going to pass this on to NSD? Do we allow this query to be answered? Or are we going to drop it? Maps in BPF are your data structures to both keep state and to communicate with user space, so you can do configuration with them. They're specific to BPF, and if you check the source code, the BPF header file, you will find plenty of different data structures made available to you. You will need special helper functions to actually do lookup and deletes, etc., etc. But this is the stuff that you need if you want to interact with what you just loaded in kernel space from user space. So the two things that we'll see, we do the state keeping, so keeping state in between packets. If you ever worked with other data plane, programmable data plane technologies, you know that it's, this can be cumbersome and tricky. But the good thing here is it's, normal C. We have created our own buckets wherein we keep track of the start time and the number of packets. And we attach that to a key, which is, in our case, a v6 or v4 source address. And now we can just count. The other use of maps, the configuration from user space. In this case, we want to exclude certain prefixes from a rate limiting program, and we do that using a different data structure that's available, a different type of BPF map that's available to us. That's the longest prefix match tree. That's already there, ready for you to use. So we make two of these maps again, one for v4 and v6, so we can exclude the ranges from our customers, for example, that we do not want to rate limit. We do need to keep a value in this map as well. And so for this, we just count the hits. So how often is a excluded prefix actually hit? How many incoming queries do we see for those prefixes? Populating those maps can be done with BPF tool, but we can also write our own custom user space program to do that, which makes it easier. So I hope that's all clear for now, because Willem will take over and show you how it's done, actually. Willem.
I'd love to. Let me share my terminal. So I'm going to show you how this looks in practice with a live demo. And I've started a virtual machine and it is running a name server. And we are under attack. It's this machine. I can send queries to it. And we are going to pretend that this machine is under attack. And I saw this presentation at the NANOC 81, and I think, well, why don't I try that response rate limiting in XDP and see if my server becomes more responsive. So let me first log into that server. So this is installing the response rate limiting by XDP from scratch, actually. So first I check out the repository, and the repository is actually has code examples for material for which we have written about in blog posts, and there's a link to those blog posts at the end of our presentation. But it's more than just response rate limiting. We have two blog posts. The first one is showing how to parse DNS packets, and the second one is about response rate limiting. So this Git repository has a submodule. Now, that's it. From the configure the prefixes which should not be response rate limited. So I have to compile this library first, because we have this user space program. If you would use only the XDP kernel space program, you would not have to do this. Here is where the response rate limiting code lives. We have 3 versions. The third version is a full-fledged version with response rate limiting as it is implemented in actual DNS software with all the bells and whistles. And configuration of it is in the source code. So you have to specify the number of CPUs. This is the number of entries in the hash table, which stores the prefixes that will be rate limited. And because we are not rate limiting individual IP addresses, but networks, which can be configured. And here is the actual number of queries per second. And I'm going to lower this a little bit for demo's sake. And the slip rate is the number of responses that will be dropped before an answer is given with the truncate bit on, so that the request will return, or the requester will return over TCP. If a requester returns over TCP, the address is not spoofed. So it's a good check. It's good to reply with the TC bit, because then there is no amplification and the requester will actually get this DNS answer. So I will first make the programs. This compiles the XDP kernel module and the user space program to interact with the prefixes that should not be response rate limited. Then I have to create the maps that Luc just talked about to communicate with the XDP kernel program about which prefixes should be rate limited and which not. And now I load the kernel module, and you can actually see by that XDP generic that Ethernet 0 now has the XDP program loaded. So let's try sending some queries. So first I will also show you the date. Nanoc.org address, and I want short answers, and also with the ignore flag to dig, I tell dig to not return when the truncate bit is received. Then sleep for half a second, and now we're done. And you see that we now receive the answers. We are not response rate limited because I'm just sending a query once half second. But if I lower the value of sleep to send more queries after each other, you will notice that there are a number of entries which do not have the answer. And those are actually the answers with the truncated bit set and without the answer. So there's no amplification, and it is response rate limited. Now to exclude my own prefix, and let's see what my address is. This is my device. Oh, not link, the address. So I'm using IPv6 to query. So I'm going to add this prefix to the very important prefixes list to exclude me from response rate limiting. Oh, add. I forgot the word add. There you go. Now every query is answered because I'm a known customer who's known to, who is allowed to ask many queries per second. All right, so that's the demo. Now let me share my presentation window. So what have we learned from this? We can leverage XDP to augment the DNS service, right? It doesn't need to be our DNS service. It could be any DNS service. And if you add this XDP module, this response rate limiting module, it will work for that DNS service. In XDP, we can either drop a packet, we can answer it, or we can send it up to the name server. Maps enable keeping state, not only for statistics and rate calculation, but also to configure the prefixes which we did not want to be subject to response rate limiting. There are different kinds of maps for different purposes. For example, the map that with which we did the rate calculation is per CPU, so no locking is needed. And if you have a mini CPU system, they can all anticipate or work on rate limiting the responses when under attack. So I'd like to talk a little bit more about DNS cookies, because it's a mechanism in DNS to generate VIP lists, the prefixes list to include, automatically in protocol. How does that work? Well, the client sends a client cookie specific for the server it's contacting. The server creates a server cookie based on the client IP, and a secret only known to the server, and returns this to the client. The next time the client needs to contact the server, it brings along the learned server cookie, and in this way the server knows that the client IP at least is not spoofed, so it's a bit like a TCP handshake, but more lightweight because the server does not need to maintain client state. So if you have a valid server cookie, you are not subjective to response rate limiting. So that means that if you do response rate limiting in XDP, you have to do DNS cookies in XDP as well, because otherwise XDP would do the response rate limiting before your name server can do DNS cookies. Luckily, so there is this call in BPF, which is called a tail call, and you can basically chain multiple XDP programs after each other. So you can create a XDP cookie verification program. We are actually about to post our third blog post telling you how to do this. And then on successful cookie verification, pass the packet to the already existing response rate limiting XDP module. Alternatively, we could also do the complete DNS cookie processing with BPF by running two BPF programs. One for incoming packets, verifying the cookies at the XDP layer, and one for outgoing packets coming from the DNS service in userspace, which will be responsible for creating the cookies. BPF programs on the TC layer are very flexible. You work with sockets buffers instead of the raw packet, and which can be resized with BPF helper functions. But it's not as fast as XDP, of course, but much more flexible. So in this way, the cookie mechanism could be added to DNS services that even do not know about cookies or do not have it. For cookies, this is especially interesting because the first implementation had different software vendors who implemented it differently and were not compatible. So in this way, you would also have a uniform DNS cookie implementation. So concluding, a lot is possible with XDP and eBPF, but it is especially a very good fit for plain old UDP-based DNS because it has a per packet processing. Right? It will be much less suitable for TCP-based DNS and probably impossible for DNS over TLS or DOE, because it's convenient to, or you have to parse the packets at the XDP layer. And we think that using XDP to augment the existing DNS service is an exciting new idea and a great new tool in the DNS operator's toolbox. We're currently also looking into offloading of XDP programs to hardware. The net-renowned SmartNICs can run XDP programs in the network card itself and doing performance measurements for that. And we're also looking ahead for AF XDP support in NSD, so completely bypassing the network stack. And also another idea we have is a hot self-managing cache, right, where the queries or the outgoing answers go into a least recently used hash map that can immediately answer those queries if it from the XDP layer, if it finds the query in that hash map. And we're also looking into load balancing zones, large zones over multiple name servers and using XDP to shard or send the queries to the correct servers. We would also like to try in the future to serve the root zone from XDP. So this was our presentation. Have a look at the Git repository and also at our blog posts and more blog posts about this will follow. And we are now open for questions.
All right, you're live, and thank you, Luke and Willem, for presenting for us on for ad-hoc 81 virtual. And I'll comment. You were both you're both coming to us from the Netherlands, which is something that would not be possible in a real world ad-hoc. And as we once we're able to move back to in-person meetings. Hopefully sometime soon. Hopefully, I can say I hope that the ability for remote participation, remote presentations such as these, will stay with us. It's been a great enhancement to the meeting, and I hope you all appreciate that. So going to questions, looks like we have one from Nate Sales. Are there any current DNS servers that support AF XDP socket communications for managing cookies within the daemon itself?
Yes, absolutely. The not DNS has AF XDP support. I think that's the only name server currently to support this. And of course, it's just as efficient to do it all in userspace once you have this direct path from the network driver to the name server software. But we wanted to focus on, if you're having an installation, having software which perhaps does not have this feature, you can use at that moment install XDP software to alter the behavior of your software. And this could include features your service would not have, such as response rate limiting or DNS cookies or padding or those kind of things.
Okay, thank you for that. The next question comes from Dan Megorian. XDP versus P4?
I can take that one. It's a short question, but let's see if I can come up with a short answer as well. P4 is a DSL, which lets you describe what you want your data plane to do, which means that you need a development suite and a specific hardware target to compile the DSL to that specific platform. So that is a big step to take, because you need to acquire specific hardware to do anything with before, and then you need to get yourself familiar with that entire development kit, if you will. And I think that's one of the biggest advantages of XDP, is that everyone, like Willem just showed, can use this. Even if you didn't think of it before and you have a running system, if it's a half-recent Linux system, you can actually start using XDP. That's I guess for this presentation in this context, the most important difference. We could talk for hours about this, and I'm happy to take this offline with Dan as well. But I see there's more questions, so maybe we can dive into those.
Okay. Looks like we've got one more. Actually, it's a two-part question from the same person. Benson Schleicher is asking if you can quantify the performance difference between XDP and a full kernel stack for simple actions like forwarding packets, dropping, etc. And any insight on improving, quantifying performance improvements on SmartNICs versus XD in the kernel for packet forwarding across a bus and similar activities.
Well, we haven't actually. We know that it can be almost line speed, but we haven't really tested for performance yet. We will do that. We have access to SmartNICs which can run XDP programs, so we will soon do that and then write a blog post about it, I suppose. But I've heard that dropping packets is about line speed, especially if you run it on a SmartNIC.
Okay, great. I believe that is the last of the questions. So thank you again for bringing this presentation, and thank you all for answering questions.